welcome to the Deep Dive. Today we're tackling a really fascinating piece of work. It's the solution that, well, basically won the AI Mathematical Olympiad Prize too.
That's right. And for you AI researchers and ML engineers tuning in, this is pretty essential stuff.
Totally. NVIDIA's winning strategy, it seems, was this powerful mix. A huge brand new math problem data set for complex reasoning, plus some, really innovative training techniques.
Yeah, things like chain of thought, tool-integrated reasoning, and also this clever idea called generative solution selection.
And they didn't stop there, right? They also turbocharged the inference with optimizations like TensorRT to LLM and speculative decoding.
Exactly. And the outcome, state-of-the-art mathematical reasoning, but in an open-weight model. It's all laid out in their paper. AIO2 winning solution, building state-of-the-art mathematical reasoning models with OpenMathReasoning datasets.
So today we're going to unpack exactly how they pulled this off, from the data right up to the deployment.
And it's really more than just winning a competition. This paper feels like a significant step forward in making this kind of sophisticated math reasoning, accessible.
Accessible, yeah.
What I find compelling is how comprehensive it is. They looked at bottlenecks across the whole pipeline, from the very first data point all the way to making it run fast.
Okay, so let's dive right into the competition itself then. AIMO-2 sounds intense.
Oh, it was. 50 completely new national-level math problems, stuff nobody had seen before.
And the constraints, pretty tight, weren't they? A 5-hour offline Jupyter notebook, just 4 L4 GPUs.
Exactly. That's not a lot of room to maneuver. And NVIDIA, well, they didn't just scrape by. They nailed 34 out of those 50 problems.
Wow, 34. That's impressive. Clearly puts them in first place.
It does. But like the paper says, their goal wasn't just about winning the prize. They really wanted to tackle the limitations they saw in the reasoning models already out there, the public ones.
Which brings us nicely to the foundation, doesn't it? The OpenMathReasoning dataset. You can't build a great model without great data. And this sounds, ambitious.
It really was. They needed a large-scale data set specifically for long, complex mathematical reasoning. They saw that as a gap.
And where did they get it?
The Art of Problem-Solving Community Forum's AOPS. It's a goldmine for challenging math problems.
Oh, AOPS. Makes sense.
But interestingly, they specifically cut out the middle school math section, decided it was, maybe a bit too basic for what they were aiming for.
Right, focused on the tougher stuff. So how did they actually get the problems out of those forums? Can't be easy.
No, definitely not just copy-pasting. They built an LLM Based Pipeline, used QWQ32B Instruct, actually, to sort of read through and identify and extract the problem.
An LLM doing the extraction.
Yeah. And as they mentioned in the appendix, it wasn't always one problem per post, sometimes multiple, sometimes none. So the LLM had to figure that out.
Okay, so they get the problems. What about the answers? You need those for training, right?
Yeah. For the non-proof questions, yeah. They used an LLM for that, too, trying to pull the final answers from the forum discussions. But importantly, they were mostly focused on just getting that final number or expression, not the whole step-by-step solution at this stage.
Gotcha. Just the target. Now, pulling data from the web, there's always that risk of contamination, isn't there? Overlapping with existing benchmarks.
Absolutely. A big concern. They tackled it head-on, though.
Oh.
They used another LLM-based comparison, basically checked their extracted questions against popular math benchmarks and removed anything that looked too similar.
Smart. Ensures the model's actually learning to reason, not just pattern matching from benchmarks it might have seen.
Exactly. That decontamination step is vital for genuine progress.
So after all that cleaning and extracting, how big was this OpenMathReasoning dataset in the end?
The final numbers are pretty impressive. 540,000 unique problems.
500,000. Wow. What's the breakdown?
So about 260,000 of those were proofs that they converted somehow. And within those, 190,000 had extracted answers, 90,000 didn't. Plus the other non-proof problems making up the total 540K.
Okay, that scale.
Yeah.
How does it stack up against other math datasets people use?
It's significantly larger. The paper shows a comparison. It dwarfs things like AOPS Instruct and the AOPS part of Numina Math 1.5. That sheer volume, you have to think, gives a real advantage.
More data, more diversity.
Yeah.
Usually leads to better models, right?
Generally, yes. And they were also really thoughtful about their validation set, making sure it matched the AIMO-2 competition feel.
Ah, okay. Tell me about that validation set. What do they put in it?
They called it CompMath 2425. They pulled problems from recent A exams, the American Invitational Math Exam, and also the Harvard-MIT Math Tournaments, HMMT, specifically from 2024 and 2025.
So recent high-level competition problems.
Exactly. The idea was to match AIMO-2 style. Similar topics, difficulty level, mostly non-proof questions needing a single numerical answer. They even filtered out proofs and partial credit questions.
Makes sense for mimicking the competition rules. How many problems total?
256 problems in that validation set, a focused, relevant benchmark for their specific goal.
Okay, solid foundation. Now, how did they get the models to actually learn reasoning from this data? We mentioned chain of thought, COT, and tool-integrated reasoning, TIR.
Right. Let's start with COT. For that, they prompted existing open-weight models, DeepSeek R1 and QWQ32B, to just solve the problems from their new dataset. Generate the steps.
And they generated multiple attempts.
Oh yeah, up to 32 candidate solutions per problem. They use settings like temperature 0.7, top P 0.95 to get some variety in the reasoning paths.
32? That's a lot of potential steps. How did they filter that down? Make sure they were training on good reasoning.
Critical step, the filtering. They basically tossed out any solution that didn't get the right final answer. They used Qwen 2.532B Instruct, again, acting as a judge, to check if the generated answer matched the expected one.
And if they didn't have an answer from the start.
Then they took the most common answer across all those 32 candidates as the ground truth. It's a clever way to establish a target.
Yeah, bootstrapping the answers. So what did that leave them with for COT training?
A massive data set. 3.2 million long reasoning COT solutions.
3.2 million.
Yeah.
Now, TIR, tool integrated reasoning. That's where code comes in, right?
Exactly. Integrating code execution into the reasoning. This gets really interesting.
So they tried just prompting for TIR solutions initially.
They did, but, well, the results weren't great. The code often wasn't very helpful. Sometimes it was irrelevant. Sometimes it just, double-checked a COT step without adding much.
So just asking for code wasn't enough. The code needed to be meaningful.
Precisely. That was the key insight. They needed to filter for meaningful code usage.
How'd they manage that? Seems tricky.
They used Qwen 2.532B Instruct, again, this time, to classify the code blocks. They looked at novelty, like, did the code do a new calculation or just verify something? And significance, was the benefit trivial, moderate, or actually significant? Classifying the purpose of the code.
Right. Plus some rule-based filtering, wrong answer, code didn't run, too many code blocks, that kind of thing. This careful filtering gave them an initial high-quality TIR dataset.
How big was that initial set?
Only about 15,000 samples, much smaller than the COT set.
Okay, 15K, that's not huge. How did they scale it up? They ended with way more TIR data, didn't they?
They did. They used this really smart iterative process. First, they fine-tuned QWQ32B on those 15K high-quality samples.
Okay, train a model on the good stuff.
Then used that model to generate way more TIR solutions, like 700,000. Filtered those down again, mainly checking for correct answers and any code usage. Didn't need the strict novelty significance filters at this stage, apparently. Got about 260K.
So use the first batch to teach a model, then use that model to generate more, then filter.
Exactly. And they even did another round. Took an intermediate 14B model they'd trained on COT, fine-tuned it on the TIR data, generated more, filtered again.
Wow, like a flywheel effect for data generation. What was the final TIR dataset size? That iterative process got them up to 1.7 million TIR solutions.
Okay, that's substantial. Very clever way to bootstrap high-quality data. I think I also saw something about controlling how much code the models generated.
Yeah, that was another neat trick. During data generation for TIR, they actually told the model how many code executions it was allowed. They'd stick a note in the prompt like, you have X code calls remaining, picking X randomly between 1 and 8.
Giving it a budget.
Sort of. And if a generated solution went over budget, they just threw it out. Taught the model to be economical with its code calls.
Makes sense. Okay, so they have this huge pool of COT and TIR data. But then there's this other technique, generative solution selection, or GenSelect. What's that about?
Well, they noticed something interesting in their results. Their models were often pretty good at getting the right answers, somewhere in the top K generated solutions, that's majority at K. But they weren't always putting the best one at the very top pass at K.
So the right answer was there, just not ranked first.
Exactly. That gap suggested potential for improvement if they could just teach the model to pick the most promising solution from the candidates it generated. That's the core idea of GenSelect.
Like adding a layer of self-critique or selection on top. How do you train a model to do that?
Another multi-stage pipeline. First, they found the default summaries from the reasoning models weren't always detailed enough for good selection. So they used Qwen 2.532B Instruct, again, to generate new, longer summaries for each candidate solution.
Okay, better summaries first.
Then, for each problem, they'd sample a bunch of these summaries, say 2 to 16, making sure to include at least one correct and one incorrect solution.
Create little comparison groups.
Right. And then they prompted QWQ32B with a specific GenSelect prompt, asking it to pick the best summary from the group. Generated about 1 million of these selections.
And filter those too.
Yep, kept only the ones where QWQ32B actually picked a correct solution summary. That gave them about 565,000 training examples for GenSelect.
Okay, but comparing like 16 potentially long summaries sounds computationally heavy for inference time.
It could be. So they made another smart optimization. They trained the GenSelect models to work directly with the generated summaries rather than needing the full reasoning traces during inference.
Oh, skip the full trace looking.
Exactly. They found using these regenerated summaries only caused a tiny accuracy drop, maybe 1–2%, but made GenSelect inference way faster.
Very practical. Okay, so putting it all together, the dataset, COT, TIR, GenSelect, this led to the OpenMath Nemotron models. What are these?
They're a series of models fine-tuned on top of the Qwen 2.5 base architecture. Sizes range from 1.5 billion parameters up to 32 billion.
And they fine-tuned them on all this data.
Yep. Supervised fine-tuning, SFT, for 6 epochs, using a mix of the COT, TIR, and GenSelect data, about 5.5 million samples total. They used unique prompts so the model knows which task it's doing.
Any special sauce in the training?
For the smaller 1.5B and 7B models, they actually started with math-focused versions of Qwen 2.5. And importantly, they tweaked the ROPE base, that's rotary position embeddings, to extend the context window. Helps handle those long math problems.
Longer context windows are crucial for complex reasoning.
Definitely. They also use standard stuff like the Atom W optimizer, cosine learning rate decay, and even average checkpoints towards the end of training for potentially better stability.
And how did they perform?
The paper shows strong results on their CompMath 2425 benchmark and another one called HLE Math. They highlight how TIR really boosts the majority at K-scores, even if pass at 1 might sometimes dip for smaller models compared to just COT.
Interesting trade-off.
Yeah, possibly because TIR solutions can sometimes be unfinished, but then self-GenSelect comes in and boosts accuracy again, especially for the bigger models.
Okay, so that's the general OpenMath Nemotron series.
Yeah.
But for the actual Kaggle competition, their winning recipe was a bit different, wasn't it?
It was. A bit more tailored to the specific demands and constraints of AIMO-2.
What did they do for the win?
They took the Qwen 2.514B base model, trained it for 8 epochs, but only on a subset of the COT data specifically, the DeepSeek R1 generated solutions, and they excluded the proofs.
Focus KOT training first.
Then, they did a very lightweight fine-tuning pass just on those 15,000 high-quality Stage 0 TIR samples. Only 400 steps. And interestingly, no GenSelect used in the final Kaggle submission model.
Huh. And they also did some modern merging.
Yes, that turned out to be surprisingly effective. They used MergeKit, a library for combining models, and found a simple linear merge like 30% COTIO checkpoint, 70% IR checkpoint gave the best balance.
Balancing the strengths of both.
Right. It improved accuracy, shortened the generations a bit, and reduced code usage compared to the pure TIR model. A nice practical trick.
But okay, the AIMO-2 time limit 5 hours, one problem at a time. Inference speed must have been absolutely make or break.
Oh, completely critical. Those optimizations weren't just nice to have, they were essential.
So what did they deploy?
A whole suite of things. First, TensorRT LLM. That converts the model into a super optimized engine, enables fancy stuff like in-flight batching, custom attention kernels, paged KV caching, basically makes it run much, much faster.
Standard practice for production, but crucial here. What else?
Quantization. They use techniques like int8 wait only, W8A16, and even FP8, which drastically reduce the model size and speed up computation, ideally with minimal hit to accuracy.
Squeezing every bit of performance.
Then maybe the most advanced bit, speculative decoding. They use something called redrafter.
Redraft?
Yeah, it's like a small, fast drafter model in this case, an RNN trained on their math data that proposes multiple tokens ahead. The main model then just verifies them quickly. If accepted, you get multiple tokens for the price of roughly 1.
Speeds things up significantly if the draft is good.
Exactly. They were getting up to 3 tokens proposed with around a 65% acceptance rate. Big speed up. They ran it almost greedily, too.
And the serving infrastructure.
They used fast API with NeMo skills, built-in time limits per problem, asynchronous generation so GPUs weren't idle, early stopping if multiple generated solutions agreed on an answer,
Smart time management.
and even straggler mitigation. Plus, for TIR, a NeMo skills wrapper around a Flask sandbox for safe parallel Python code execution with timeouts and call limits.
Wow. That's a serious engineering effort just for inference.
Absolutely. Full-stack optimization was key.
Which makes their discussion about the actual Kaggle outcomes really interesting. It wasn't all smooth sailing despite the tech.
No, it sounds like it was pretty nerve-wracking. They mentioned the high variance on the public leaderboard, just 50 problems. Random order made it hard to know if changes were actually helping.
Luck of the draw on the public set.
Right. And they also found that sometimes smaller models, like 7B, did just as well or better than their 14B Kaggle model in their own testing. But that didn't always hold up on the leaderboard. Maybe differences in the hidden test set or specific problems hitting weaknesses.
Frustrating when local results don't translate.
And one key learning seemed to be that their final models generated longer solutions on average, which actually hurt their time management strategy in Kaggle because that strategy relied on solving easy problems quickly first. Longer solutions ate into that time buffer.
An unexpected interaction between model behavior and competition strategy.
Yeah.
Fascinating real-world stuff.
Definitely. The paper also briefly touches on related work just to position themselves.
Right, situating it in the field.
Yeah, mentioning things like program of thoughts, other tool-use datasets like OpenMath Instruct 1, Infinity Math, also nods to using LLMs as judges and other big math reasoning datasets that have come out.
Good context. So we had to wrap this all up. What are the biggest takeaways from this deep dive into NVIDIA's winning solution?
I think there are a few really key contributions. First, this novel way they combined code execution with CoT to generate high-quality TIR data using that iterative filtering approach. That's really innovative.
Yeah, the TR generation method was clever.
Second, the GenSelect pipeline, training a model specifically to pick the best solution from candidates. That's a powerful idea.
Improves the final output quality.
Third, and maybe most impactful for the community, is the release of the OpenMathReasoning dataset itself. 540K problems, carefully curated. That's a massive resource.
Huge contribution, releasing data like that.
And finally, the OpenMath Nemotron models themselves, state-of-the-art open-weight models that can do SUTI, TIR, and GenSelect. They've really pushed the boundary for open-source math reasoning.
Absolutely feels like a leap forward. And the best part for our listeners, especially the technically inclined ones, is that NVIDIA released pretty much everything.
They did. The code, the fine-tuned models, the entire OpenMathReasoning dataset, it's all out there on Hugging Face and GitHub under a permissive license.
We'll definitely put the links in the show notes. It's https://huggingface.collections, NVIDIA OpenMathReasoning 68072C0154050999573D 2TT730, https://huggingface.coco_collections, NVIDIA OpenMathReasoning 68072C0154050999573D 2 and https://github.com/NVIDIA NeMo skills. https://github.com other NVIDIA NeMo skills for anyone who wants to dive in themselves.
And looking ahead, thinking about those tight AIMO2 constraints and all the inference optimization they needed, it really makes you wonder, doesn't it? What are the next big bottlenecks we need to crack for deploying these kinds of advanced reasoning models in real-world, resource-limited situations?
Yeah, where does the research go from here? How do these techniques evolve?
It's a great question. How do we make this kind of power even more efficient and robust?
A perfect thought to leave our listeners with. Well, thank you for joining us on this deep dive into what is, I think we can agree, a really groundbreaking paper.
My pleasure. It was fascinating stuff.
We hope you found this useful and insightful. As always, we love hearing from you. Let us know your thoughts, feedback, or suggestions for what we should cover next. Until next time.